Hi, everybody. This is lecture 22 on smart pointers. Lecture 21, previously we had looked at building our own smart pointers. So today we're going to look at the smart pointer set that comes from the memory library. It includes unique pointers, shared pointers, and also something you don't see here on this first slide called weak pointers. So first I'll do a quick review just to get everybody back up to speed again since our last lecture. You may recall we talked about an idiom called resource allocation as initialization. It's also referred to as RAII. It's a terrible acronym. Sometimes referred to as scope-bound resource management. This is the idea of just building a class that knows how to manage its own memory allocation and deallocation. So when an instance of the class comes into scope or gets created on the heap, it does all the management that it needs to do to create things and delete them when that instance of the class goes away. So it helps us prevent memory leaks and cleans up after itself, so it's well behaved. And often these kinds of classes need to have custom developed copy and assignment operators inside the class. And sometimes that's referred to as the rule of threes: a copy, an assignment, and a destructor. Those things often go together, and sometimes many more things. So we're quite familiar with this behavior. All the containers that we've worked with in the past have implemented this, like vector and array and maps. They just work so well, we don't know they're actually doing it, which is the whole idea. So today we're going to look at shared and unique pointers, and if we get time, we'll look at weak pointers as well, which are all part of that smart pointer set. And we'll dive into that. So a quick review. When we wrote our own version, a little mini version of smart pointers, we used the star operator, or the overload of the star operator, to implement this idea where an instance of a class could actually act as if it was, it understood that it was a pointer. So we could dereference it with the star. Even though it was just an instance of the class, overloading that star operator allowed us to make it act like it was a true pointer, which was very nice. So we could do something like this. We could create an instance of our class smart pointer. We'd call that instance SP, and we'd feed it a pointer to a new integer. So you see there that new int 5 goes on the heap. That passes a pointer into the constructor for SP. And then we could try to print out that class if it was printable. But really what we would want to do is to print the dereference to that class. And again, usually star SP wouldn't work because SP is an instance of the smart pointer class in the stack. But since we've overloaded that star, we're saying, hey, give me the pointer that, or give me the thing that the pointer refers to that I'm managing. So that PTR, private variable there, what that's pointing to, star SP is interpreted as meaning give me that thing. So it just returns what the raw pointer points to. So that's the key piece that we began to explore by overloading these operators in our own custom version of this. And we can even do things like that where we can dereference and add things together. And if we used a reference on our operator overload, we could actually make an assignment to that location, which is pretty cool. So all these things make the instance look like it's behaving just like a pointer, which is one of the powers of being able to implement this kind of strategy. So, so that was our kind of approach. We also kind of said that one problem with this is that we can run into troubles if we try to copy these values over one another. So in the case where we have two of these pointers that are managing two different pieces of data on the heap, we could run into some trouble when we try to make assignment or use a copy constructor kind of situation if we're not properly managing the deallocation of memory. And when we talk about shared pointers today, we'll actually see how they deal with that problem much more elegantly than what we implemented the other day. Otherwise, we just had a relatively simple way of doing this kind of thing. So today's smart pointers, just high level, it's a collection of pointers of various types that come from the memory library. So if you want to use these, you have to include the memory library. And unique pointers is a shared or is a smart pointer rather that only allows you to manage one thing on the heap using a specific instance of the unique pointer class. So it's one-to-one, right? So you can never have two things pointing to the same chunk of memory on the heap. Shared pointers, however, do let us do that, and they include more management code that allows you to copy and assign these things. Basically, the shared pointers keep count of how many references are being made to a unique chunk of data on the heap. And that inclusion of the reference counting that we'll talk about later on in the lecture lets us defer deletion of something on the heap until the last shared pointer goes out of scope. So that's a really powerful concept. And then weak pointers is a little bit of a special case, but it allows us to sort of monitor the situation with shared pointers, resolve a few gotcha cases that can come up in complex coding situations where they don't affect the reference count. So it's a bit of a corner case, but important to know about. So we'll cover all those today. And we'll start with the unique pointer, which again deals with one-to-one correspondence between an instance of the unique pointer class and what it's trying to manage. So here's the problem we're trying to deal with. We have a foo class F1, we pass a constructor value in there. And so if we have a foo class that has a pointer kind of that points to some data on the heap, we now have F1 on the stack, and what that foo class is managing on the heap is there on the right in the orange, right? So we can do that again with F2. But if we did something like this, where we said, hey, I just want to use the assignment operator, system level assignment operator, and copy everything from F1 over to F2. So that's an assignment between two existing instances of our class in the stack. That's going to create some problems because it's going to just do a value by value copy between the instances of F1 and F2. And now we see we've kind of lost a handle on the heap instance there, and we really need to preserve that to avoid having memory leaks, right? So that's a problem. And then also it turns out that now that you have these two pointers pointing to the same thing on the heap, it's entirely possible that one might delete the data on the heap and the other might not know that got deleted. So we could have a crash if we try to access the pointer after someone deletes the data on the heap. So this is the problem we're trying to solve. Unique pointers solve that by enforcing a one-to-one correspondence. You're literally not going to be allowed to do an assignment operator or even a copy constructor between classes like this when you're using a unique pointer, and that's its way of solving that particular problem. We'll see that the shared pointer goes about it a slightly different way. But for the unique pointer in this shared pointer, or in the smart pointer library, we actually don't have a copy or an assignment constructor, right? So that's kind of what we're dealing with here. So we create an instance of a unique pointer, and we actually have a template, which we didn't do with our smart pointer class in the last lecture. So we can now create a unique pointer to any kind of object using, or a data type using a template. And we have formal management of that dynamic item on the heap. So if it's an integer we're dealing with, we get an integer on the heap that's being managed. It could also be an instance of a class called foo, for example. And we'll initialize that at construction time. And with unique pointers, generally we can never change that unique pointer after it's been instanced, except through some very special operations, which we'll talk about, which are move and also swap. We'll talk about those later in the lecture. And as I mentioned, the system level copy and assignment operations for the class have been removed. So if you try to do some basic copying or assigning, the compiler is going to catch it and warn you about it very, very early on. But otherwise, when we delete the unique pointer, if it goes out of scope, it's going to manage and clean up the data that's on the heap. So in other words, it's going to get rid of that int5 if our U pointer goes away. And it's been highly optimized. So basically, there's no cost to doing this. There's no argument not to use a system like this, at least for unique pointers, because it's very optimal. It definitely helps minimize bugs. So unique pointers are popular for large-scale development. Not everybody's adopted them, because there's a lot of legacy code out there, obviously, but if you're starting a project from scratch, it's something that definitely should be considered, right? It implements this idiom, resource management is allocation. So that's kind of where we're at. Just reviewing what we did the last lecture, we created our own class called Smart Pointer You may recall that was our class type, smart pointer, or class name. We had the name of an instance that we're creating, and then to its constructor, we passed a pointer to an integer that we created with the new keyword. So new int1 created an integer on the heap, passed the pointer into the constructor of our new pointer instance, right? And then and what we did in our last lecture, we created a little private pointer that managed that for us. We didn't have a template type there. We were just dealing with integers in our last lecture to keep our examples somewhat simple. But now that we're moving into the standard library implementation of unique pointers, we've got the advantage of being able to have a template there. So here's what the equivalent looks like for our unique pointer, right? So here's unique pointer class name. There's the template type that we're going to manage. There's the name of our instance. And once again, we're just passing in a pointer to a newly allocated data item. In this case, it's an int, and we initialize its value to 1. And that has to match the type in the template over here, right? So if we did a class, it would look a little different. We'd have foo maybe, and then foo constructor and arguments there. But this is just a simple data type example. But the nice thing is now with unique pointer, we have that template specification. So we can manage any kind of pointers this way, which is great, right? But these two things have to match. So here's how we would go about creating a unique pointer with an instance. There again is our class name. There's our type that we're going to be managing, our instance name. And then, as I mentioned on the previous slide, we can pass in an instance of foo, but we do have to call its constructor properly. If it has a default constructor, we can leave off those arguments, but otherwise we can pass in the arguments for the foo constructor here. And what we're passing in is a pointer to an instance of foo that is on the heap. The unique pointer manages a pointer. So we would not be trying to pass in foo of x. We would be passing in new foo of x all the time here, right? So with that, I'm going to pause and we'll switch over to the second half of the video, which you'll get a link to so you can continue this. Thanks. So we're recording this just so everybody knows. Right, so this is our unique pointer, right? And it's constructed the same way we were building stuff the other day. So should be pretty familiar except for the addition of this template type, right? So, but the key thing is that the type of the template needs to match the type that you're putting on the heap. When I say new int, then this type over here is going to be int. If I am creating a pointer to an int on the heap, then this would be an int pointer. But I'm creating an int on the heap, so it's int and int. And that's an understandable point of confusion, but that's kind of how these things work. So if we were to put a class, if we were to create a unique pointer to an instance of a class, it'd be something like this. We have our class type, which is unique pointer, the template, which is what is this pointer managing, what kind of data, it's an instance of foo, the name of the variable, if you will, so it'll be the name of my instance of unique pointer, and then the constructor, or sorry, how I'm going to call the constructor with new, because I want to pass in a pointer to foo, right? So this is not just foo of x, it's new foo of x, which passes in a pointer to a newly constructed instance of foo. And these are the constructor arguments for foo, right? So it's very similar to what we were doing. It's just that we now have this template access that we can use. And of course, we have all of the niceness of this stuff being developed for us and debugged and everything. So let's take a look at a couple more of these. So unique pointer of int, and my nomenclature here, U means unique pointer, underscore null is just a reminder that we created that thing null, but it doesn't always have to stay null. So, and then there are things that we can do with our unique pointer where we can test the class name itself. So that it has an overload for these parentheses where we can evaluate the class, the instance itself to determine whether it's a null pointer or not. So we can say, hey, if this null pointer is basically, knotted, if it doesn't exist as a pointer, then I'm just going to print out the word null, right? And that's true because we really didn't assign it to anything. We didn't give it a constructor, so we didn't create an int that it's managing on the heap. So that's kind of where we start with that one. Now contrast that to this case, very similar, another unique pointer, but we're going to pass in a new int with a value of 5, right? So this thing actually now is going to be managing on the heap a pointer to int 5. And if you try to take that same pointer, so let's say you had that same pointer to that same chunk of memory somehow, and you were to try to feed it to another unique pointer, it would cause us some serious problems. But the unique pointer is going to do everything it can to prevent you from copying that thing around, right? So this thing we can say, hey, if it's defined, if it's not null is basically what that's saying, then go ahead and print out what it points to, right? So star UPTR should print out 5, really, because that's what that pointer is pointing to, okay? And then we could do that too, right? Assuming that that thing is non-null, right? And then we can reset. There are a number of methods on each of these pointer classes. So I can say uptr.reset basically says just delete that thing on the heap and set that pointer to null. I'm done with that thing now, right? So that's one method you can actually call, which is pretty useful to have. And then if we were to try to do star u pointer after that, we'd have an error, right? Because that's essentially trying to print out a null pointer, okay? But we can still test it and see if it is null before we try to use that pointer, which is always a good idea. You have to do that anyway when you work with pointers. So that's our kind of introductory pass on the unique pointers. Anybody have any questions on that? Just kind of the concept, how it maps to the stuff that we were doing previously. Just want to make sure that I haven't lost anybody too quickly yet. Okay, everybody comfortable with that? Cool. All right, well, let me kind of move on, then we'll kind of move in the direction of our first practice. I think we're going to look at one more example here, though, of doing this with an instance of a class. And the reason this gets a little confusing when you move from an int type to a class type is a lot of our classes need arguments for their constructors, right? So where do we express those arguments? So here's a simple case. We're just creating a null pointer, a null unique pointer to class foo, right? Well, there's no instance of foo over here because it's null, but we have designated that this unique pointer will and can only ultimately ever point to an instance of foo. So that's what the purpose of that. So I can test for null if I want. I can also now create a unique pointer that is not null by feeding it in a pointer to an instance of foo. And the way we have always learned to create instances of a class is to name the class and then pass in whatever arguments it has. So this is basically just invoking the constructor with the new in front of it sufficient to get a pointer to that instance on the heap. And now that pointer passes into the constructor of uPointer and becomes a private member of that, just like we saw on Tuesday when we were creating our smart pointer, right? So that's really all we're doing. We're invoking this inside of these parentheses to create an instance of foo on the heap, passing the pointer into the constructor of uPointer, which now is going to manage that for us, right? So that's what that looks like there, right? And we can test that one as well. We can say, is uPointer null? If it's not, then I'll go ahead and print out what it points to, right? That's all totally fine. And then I can still reset that. And here, when I reset that, it's forcibly saying, delete what's on the stack and set yourself to null. It could also go out of scope, right? If this was all inside of some block parentheses and uPointer went out of scope, it would all automatically call its destructor. And when the uPointer calls its destructor, guess what? It's going to, of course, destroy whatever it's pointing to because it's going out of scope. Because it's a unique pointer and it knows it's the only one that's ever going to be pointing to that thing on the heap. So it says, oh, well, I'm going away, so I'm going to go ahead and delete that thing on the heap as well. Okay. So that happens again. That happens whether you explicitly reset it through a method or whether it goes out of scope. Okay. And then if you try to print that out, of course, you would have an error, but you can test it beforehand all the time. Okay. So that's unique pointer with an instance. Now, this just recalling the obvious, right? And I think I probably hammered this home a few times, but you should realize by now that uPointer is not actually pointing to foo, right? It's an instance of a class, a unique pointer class, and it has a private pointer that it's hanging on to that is pointing to this foo instance on the heap. And then it's, of course, doing all those things that we learned about on Tuesday, but it's not a pointer. We can treat it as a pointer, right? We can even do that. We can say star U pointer equals some instance of foo, all of those typical tests, because all of that stuff has been overloaded, including the arrow, right? So we can get at members of the foo class if we need to, like the val, through the arrow. All of that is done through overloads of those operators, which we saw on Tuesday, okay? And it just makes us think it's a pointer. It's not a pointer, really. It's just an instance of a class, okay? Which is nice. It's nice that it can actually work that way. And there is a key thing that this might seem super obvious, but it will trip you up from time to time. When you see something like a U pointer or an instance of a smart pointer dot something, we're calling a method that is a member of the class U pointer. That is very different than saying U pointer arrow val. Since arrow has been overloaded, we're reaching into the piece of memory being managed by the U pointer and getting its a member from that class, okay? So this is really calling, the dot is calling a method that's a member of the U pointer class. The arrow is going right through the raw pointer and getting at some sub value that's a member of assuming it's pointing to a class, it's the class that we're pointing to, okay? So that's subtle, but it's one that might come back to puzzle you from time to time, because a lot of people, what they'll do is they'll forget and they'll try to say U pointer arrow reset. And of course, it's going to blow up and say, hey, the foo class doesn't have a method called reset. But if you do dot reset, it will say, oh, well, that's fine because U pointer is a unique pointer class and it has a reset method. So it's really important to realize the difference between what's going on there and there, okay? And then if U pointer is overloaded, this if test is an overloaded operation we can use to test the value of the pointer, whether it's null or not, okay? So that's kind of maybe obvious, but. So here's a couple scenarios you might see in code. We can create a unique pointer of type int. I'll call it I_ptr1 just to remind me that it's an integer pointer. And then I'll pass in a new int on the heap, okay? I pointer 2 gets an integer to pointer 2, okay? And then I can try to see if these things are equal. I can say, is the address of this instance equal to the address of that instance? Well, it's not, right? Because these are two different classes on the stack, and the addresses of those classes are not going to be the same, right? Those two are not going to be the same. We can check the value and see whether the value of something is equal to the value of something, right? But we can't expect these two things to be equal, and we also can't do an assignment here, right? We can't say, hey, I've decided that I want I pointer 2 to be equal to whatever I pointer 1 is, because we've thrown away the assignment operator, okay? So that was an assignment operator type of attempt, and because we've deleted that in this class, we can't do those kind of assignments. And why is that? Because the people who designed the unique pointer didn't want that to be able to be done, because everybody should only be pointed to by one thing, okay? Now we can reconstruct, there is a way to forcibly reconstruct, you know, a new pointer, right? In which if I say I pointer 2 equals something brand new, that is going to release this integer here on the heap, this int2, it's going to delete it, and it's going to reassign this to something like a integer 20 on the heap. Okay, so there's a way to reconstruct it, but you can't copy or assign things using those type of operators, okay? So right. I think we covered that point there. So pausing just for a second, any questions on that? I know that's kind of a lot of stuff, but curious if you guys, anybody's got some questions on that. Okay, cool. There's certainly a lot of syntax there. I'll try to give you time to digest that as we go along. Okay, all right, so let's take a look at our first exercise with unique pointers. And these things, I'll tell you up front, it's a little hard to come up with, you know, easy, digestible exercises that don't seem pointless. You know, like when you're dealing with pointers, unless you're building a large system, it can be a little hard to track stuff. So bear with me while I take you through these examples. Some of them seem a little silly, but what I'd like you to do in this first one is just create 4 different kinds of unique pointers in the REPL, right? These different types. So an integer, a double, a string, std string, and then some instance of the class foo, which I've written for you in this REPL. And then we're going to do something kind of silly, but we're going to try to add up the values of all the things that are pointed to by each of these pointers. Now, some of these things, like integer and a double, you can add. You can say, give me what I unique pointer points to, and give me what D unique pointer points to. But when you get to a string, we need to use the arrow to get the size of the string. So we're going to add up the length of the string as part of its integer number. And then for the foo class, we're going to say, give me the value of foo. So FUP, or foo unique pointer arrow val, gets the value. So your goal is to just exercise accessing what these pointers point to. And in the case of these two data types, you have to realize you don't use the dereference star, you use the arrow, right? Because here we're getting at a method, and here we're getting at a value. Here the method is a member of the string class, which is what we're pointing to, and here the value is a member of the foo class, okay? So that's what we want to do. Give that a look and just double check, make sure the sum makes sense to you. And then the last thing, try to reset that unique pointer that owns the foo instance and see what gets printed out. And the hint is that the foo destructor, it has a little message in it. So anytime an instance of foo goes away, that destructor is going to chime in and print something out to let you know that it just went away. So check that and see if that all makes sense to you. I'll give you a couple minutes. And just jump in if you have any questions at all. Okay, thanks. And I'll leave my mic on. Yes, good question. Please include memory. Yeah, I think I left that out on purpose to raise that question, but I forgot to mention it again. So yes, so in order for you to get access to all of the, or that unique pointer type and all of these shared smart pointer types, you'll need to include memory. Thanks. And I'll roll back so you can see some of the syntax on the previous page. In case it comes in handy while you're doing that, okay? Set my timer. Again, if you ever get confused about what syntax needs to go inside of the parentheses here, these parentheses are the constructor for the unique pointer, and that always needs to get a pointer to the same data type that you've put in the template there, okay? And in the case of a class, if this was a foo class, then of course what goes in the parentheses here is the constructor arguments for foo, if it needs any. You know, I just realized, by the way, sorry to interrupt you guys while you're in deep thought. It seems pretty silly, but I never realized you guys can't click on the links on these because it's a video stream. That's got to be a real hindrance for you guys to try to get access to these replets. That's a little silly of me to not realize that. I'll have to come up with a better solution for that. Obviously, you can download the slides, but keeping track of that would be good in some other way. Yes, yeah, and some sort of, go ahead.
as someone who has been doing a lot of live streaming for work, what I like to do if I have links that I need to give out is I take them and put them into a text document, and then I copy and paste them as needed into the chat for everyone.
Oh, that's a great idea. Thank you. Yeah, yeah. I'll do something like that because yeah, I think obviously without being able to click on this stuff, it's just about impossible to type it in by hand, and I'm sure that doesn't make it very easy to do these exercises. So sorry it took me that long to realize that. Good suggestion. I'll get that organized for the next lecture. Oh, and actually I can probably just do it as we go along here as well. I think I can do that without, let me see if I can do that without, yeah, I think it looks like it's a little problematic, I guess. But I'll see if I can't remedy that situation as we go here. Okay, so let's take a look at the solution there on that guy. So we're going to just get my windows organized here. So there's our unique integer pointer pointing to 12. I picked 12. You could pick anything. There's our double pointer, shared or unique pointer pointing to a double value of 1.4. And then here's our string. This might seem a little confusing because we don't often use, initialize a string container this way, but you can, of course, just say, I want a new string container, and I pass into the constructor for the string container the hi there string, right? And then that pointer to that string container gets passed into this instance of the unique pointer class, right? So we're creating a new string on the heap. We pass the pointer in, which matches this type right there, okay? Question one. After the new keyword, can you value initialize it? You mean like with the braces syntax? Good question was whether we can value initialize it after the new keyword. I don't think, oh yeah, can we value initialize it? I don't think so. I mean, if it's a primitive value, I think you might be able to, but with a class, you really just have to pass it in through the constructor. Although I don't, maybe I'm misunderstanding the question, but yeah. Oh, okay, so that one, thank you. That works. So I mean, you can do it through the constructor, of course, that way. Maybe that's what you mean, but other than that, you can't do anything else. Right. Okay, so a couple other things. Let's just click through this. So, so we can't construct the unique pointer based on a copy of a previous unique pointer. So that's not allowed. So even if this was compatible, right? Like if we're passing in a pointer to an instance of foo or some other foo, rather, sorry, a unique pointer, we can't do that because the copy constructor has been deleted. And similarly, we can't, that's a copy constructor attempt as well. That's just another format for the same thing. And then this would be the assignment operator. So we can't do that either, right? So those are the things that the unique pointer will not allow us to do. But we can then go ahead and add these things up. And again, we just use those references, as I pointed out in the previous slide, and then reset. And the key thing is that when you reset, you're going to see that destructor for foo get invoked, right? So you'll see foo telling us that foo's going away, because when we reset f_up, it's explicitly deleting that instance of the unique pointer, and thereafter it's going to automatically clean up whatever it has managed on the heap. Same thing would happen if that just went out of scope. In fact, for any of these things that we create up here, you'd see it when it reaches the last brace in main, those things are going to go out of scope and it will trigger the destructor message. So let's see, and those are kind of the observations just kind of written down for you if you want to come back later to kind of see these things. One thing to keep in mind that this star up in parentheses dot size actually works, so we can sort of extract what up points to and then invoke a method or a member from a class by using the dot, which is the same way we would do that kind of hacky approach with pointers, but just to say that it actually works to do it that way as well with the unique pointer if you want to. Okay. Any questions on that? Okay, so let's take it up a notch just a little bit and think about what we would do if we wanted to manage a vector of smart pointers, right? So we've done, actually, I don't know if we've done any vectors of pointers yet. You are in homework 7 for your grid, creating a vector of pointers to tokens, which is cool. But we're talking here about just a 1D vector of smart pointers, right? So how would we do that? Well, remember we looked at these examples a couple lectures back. These are the 4 practices we did where we created a number of different data structures. And so what we're asking here is actually kind of number 2 and number 4. Like, how would we convert this data structure to be using unique pointers or shared pointers, any kind of these smart pointers, right? What's the right way to do that? Because if you remember, what we had to do in these cases was we had a raw pointer and we had to dynamically allocate an array on the heap, and then we assign pointers to each position of that array. And so there's kind of 2 ways you could go about doing this. One is definitely the better way, but let's consider kind of the simpler approach. Or let's take our puzzle constructor, because this is a little bit of a look ahead to homework 8. So the next 3 slides is a little bit of a hint for when you do get to homework 8. Don't worry about it if it doesn't, all sink in right now. But the idea, if you think about our homework 8, right, we've got this pointer to a token. We call that pieces. So that's a raw pointer, right? It's our old style pointer. And then we do have a vector of token pointers, which is also kind of our old school pointers. And then our dynamically allocated array of token pointers. So this is what you're going to be working on for your constructor, for your puzzle instance in homework 7, right? So these are all old style pointers, and that's what you should do for homework 7, right? So that's what you're going to do. But what if we wanted to convert all that, once you got it all working, to switch it over now to shared pointers? Well, what would be the best way to go about doing that? So for the moment, we'll still keep our raw pointer there in main, but here's our class, right? And so we could keep the old style raw pointer and of course our grid and create that dynamically allocated array of smart pointers, right? So we could kind of go half and half. We could kind of dynamically allocate this thing in red, but then use it using old school pointers, this old school pointer here, and then fill it up with these smart pointers. And then, you kind of have this mixed bag of old style and new style together, right? So we kind of half converted, but it's not really the good way to go. It's really rather messy in code when you really get down to it. So generally the school of thought is if you're going to go do things the modern way, you should go all the way, right? And so this is really kind of the messy solution. The better way to do this, and again, this is the big hint for homework 8, is that we would, at least inside of our puzzle class, create a vector of smart pointers to tokens, okay? So it'd be a vector, and then a vector of smart pointers of tokens. So the first one is our pieces, and the second one is our grid, right? And then when we actually when we've converted that over, we essentially just have to push back smart pointers into this vector, right? So rather than dynamically creating this array of token pointers, we just do a pushback. But what we're pushing back now would be smart pointers, right? And we have this modern vector of smart pointer tokens over here that just makes all of that so easy for us to do, right? So that would be the best way to do that, is to convert everything over. And really, we should convert this whole thing in main over to be a smart pointer as well. And that's really what homework 8 is going to do. So once you kind of get homework 7 under your belt and we kind of play around with these pointers, one option you will have on homework 8 is to just convert that thing over to shared pointers, and you'll be done with homework 8. You can also do an alternate homework 8 as well that we'll talk to next week sometime or the week after, which is more of a Facebook thing. So if you're tired of this whole jigsaw puzzle thing, you can take a different path. But this is kind of what we're talking about today. If you want to put it in context, you can kind of think about your homework 8 this way. But let's do a simpler version of that. We're going to try to just create a dynamic array of int pointers, right? And so we're going to go with the container. We're basically going to follow our own advice here and say, let's create a container where we push back into that container a bunch of shared pointers, right? So this is what our container would look like. And it looks a little intimidating at first, right? But if you break it down, it's not too bad. So basically I want a vector of pointers to numbers, okay? Or to integers, right? And so I'm going to create a vector, but we know vectors need a template, right? And so what kind of thing are we pushing into that vector? Well, we're going to push unique pointers into that vector. Well, what kind of unique pointers? Well, those things are templatized too. So that's an int type of unique pointer. Okay, so it's kind of a lot of syntax, but if you break it down, it's not too bad. It's just a vector into which we will push unique pointers of type int. Okay, and in order to do that, all we have to do is say num pointers dot pushback. So num pointers is the vector. Pushback is a familiar method we know. And what we feed to the pushback has to match this type, right? So it has to be a unique pointer of type int. And as we have learned just recently, we can pass in a new int of some value into that unique pointer. So now that unique pointer is managing some temp int or 5 or 2 or whatever integer we put in there on the heap, okay? So that's how we would just push back one shared pointer into that vector, right? So that whole thing creates an instance of a unique pointer. That's what we're pushing back, okay? So it's something like that, right? But those things that are pointing, they're all shared pointers pointing to an int on the heap, okay? So let's take a look, just break it down. There's the vector type, the type that we're pushing in, type of our unique pointer, and then the name of our container or our variable that we're going to be dealing with, okay? And let's see, I think there's a few other things here. There's just a pictorial version of that to make sure it kind of sits with everybody. So here again is that code bit. We could say num pointers push back unique pointer of int, and then we give it the specific integer we want to put in. That could be some variable or a constant, like in this case. And so that's going to push it in there. Now, if we put it inside of a loop, right, we're essentially just shoving these things into a container. So there's a way we could iterate over the top of everything. It's a little bit out of sync. This should really be below this pushback thing. But if we had pushed back 5 of these things, we could actually iterate over the top of that container and print out whatever was inside of that container. I apologize, this for loop should go under that num pointers pushback piece. But this is basically that same old container iteration that we've seen many, many times, where once we've filled something up, we can iterate over it and get Q out of it by going from begin to right up before end, okay? That's one way we can iterate. We can also use the range-based for loop to iterate over the top of that container. We've seen both of those ways to do that. Questions on that? This idea of putting shared pointers directly into a container, this would be the more modern way to do things. Everybody okay with that? Okay, all right, well, let's see if we can kind of do an exercise. This is all the same old stuff we've seen, right? So we could say if num pointers of I, in other words, if the shared pointer at a particular location of I is not null, then we can go ahead and print out what it points to, right? So we can do that by virtue of the fact that num pointers is holding a shared pointer, and we can evaluate that instance and it will determine whether the pointer is actually null or not on that pointer. I keep saying shared pointer, but it's a unique pointer in this case, right? And I can also say if what Q is pointing to in the iterator is not null, then I can say star Q arrow num pointer. This is a little confusing because iterators, you recall, are themselves a class that has an overloaded star pointer on it. And so we have to dereference the Q and then use the arrow to get it to num pointers. So we won't do it this way in the code. This is kind of the tricky way to do it, but I just wanted to put that up there to let you see that. Okay. Any questions before we move on to the exercise? Okay, let's give it a try, and I'll see if I might have to pause the screen. Oh, we'll look at a little more code here, and then I'll send you guys the link in the chat room here. So, but here's just a little more code that you might need in your exercise, right? So push back unique pointer, we saw that. Num points clear. We'll actually clear the entire container, which actually deletes, not only deletes the pointers, but frees the integers off the heap as well. So you're going to find in homework 7 that you have a non-trivial amount of work to actually walk through and delete and deallocate all your tokens. This would do all of that for us with one piece of code, because all of those things have destructors and they get called in order, and it cleans some things up very nicely. So this is really one of those definite benefits of this scope-bound resource management strategy. Okay. All right, so let me see if I can get this link over to you guys. So let me pause that, copy the link over to the chat room, and send this out to everyone. So there's our practice link for this one. See if you can get into that one, okay. And then while you're doing that, let me just get I'll get the solution link as well for when you're ready for that one. And I'll put that out there too. Okay, and then back to the presentation. Okay, so give that a try. I'll set the timer. I'll put the code up here so you can kind of look at, sorry, go to the slide just before the practice. You can kind of see some code samples there. Oh, did it again, right? And I'll give you a couple minutes on this, and then we'll go through the code together. Okay, I'll go back to the practice just so you can see what it is we're trying to do here. So this may remind you of that exercise we did 2 weeks back when we first, or a week ago. So we're just trying to add up a bunch of numbers that the user inputs, but this time we're trying to store them using these unique pointers. Okay, maybe another, a little less than a minute. Okay, let's take a look at the code, talk a little bit about what's here. Screen off a little bit. So, right, so in this first chunk here, we're going to create our num pointers. This is the array of shared pointers that we're going to push back into the vector, right? So we'll prompt the user for how many pointers they're going to create, or how many numbers they want to create. And then for each one of those, we're going to further prompt the user to enter a number. And I've just sort of stored it in this temp integer here. But so each time, this is the code that might just seem a little intimidating. Each time we go through that loop, we're going to push back the creation of a new unique pointer of type int, which means it's managing an int on the heap. And then we have to pass in a pointer to that newly created int. So we say int, and then we do that initialization with temp int value there. So that's that part. And then if we want to iterate through it, and this part is a little tricky. So rather than iterating through with that, with the iterator, I use the range-based for loop here. And so what we've done is we're saying for each shared pointer, and notice I use the auto, right? That's really nice because I don't have to put in all this unique pointer underscore int type. I just say auto ampersand p. Remember, the ampersand means we're getting a reference to that pointer, so we're not making a copy of it, which would be a problem. That would probably create a problem for us because we're not allowed to copy those things. So we do a reference to that shared pointer from the vector num pointers. And then we say sum, which is just our counter, equals whatever it was plus what p points to, right? So that's getting the value from that shared pointer. So it's really very much like a normal bit of code. In fact, you know, there's nothing here that you would need to change in this little piece of code if this was a raw pointer versus the shared pointer. That's the really nice part about this implementation, is that part of the code is really the same. It's just the way you instantiate them in the beginning that actually changes. Okay, and then we can go ahead and print out our sum, and then we can just clear that num pointers container, and it'll get rid of everything on the heap for us, which is just really nice. We don't have to walk through and find it and delete it. It does everything for us automatically, which is great. Okay, any questions on that? Okay, cool. All right, well, let's kind of move on then. So here are just the insights. If you come back to this and you just need a little few reminders on what's going on here, hopefully this will be helpful for you. So kind of wrapping up our unique pointer overview, and this will be the same for shared pointers for a lot of this stuff. So this is the way we have some type T kind of represents any arbitrary type. That's the way to create a null pointer, or we can create a new something of that same type, whether it's an int or foo or some other class or even a vector. And then these would be the arguments that go to that constructor. Or if we're going to initialize an integer, for example, we put the value in there. Right? And we could similarly just save ourselves a headache and say auto, right? And let auto figure out what all of that is based on the constructor. That's the interesting thing. What you're doing here with new actually specifies what kind of unique pointer we're actually creating, and it gives auto an opportunity to figure all that stuff out by itself. So you could do it that way if you want as well. That can be a lot less intimidating. And then we can say, okay, well, if that unique pointer is actually pointing to something, then let's maybe go ahead and print it out, right, using star up. Right? Now I can get at the raw pointer if I want, and this is true of the shared pointers and the weak pointers as well. If for some crazy reason you need to get at the actual raw pointer, the raw address on the heap, so you can go do something to it, you can do that. And so that method lets you get that raw pointer and do something with it. Okay. You can also swap with some other unique pointer. That's kind of a special operation that allows you to modify unique pointers. It's kind of one of the very few ways you can do that. There's something called move that'll let you do that as well. But you can't do anything like that. You can't actually pass in another unique pointer into the constructor for this newly created unique pointer. That would be a copy constructor violation. And since we've got no copy constructor, that's just not going to work for us, right? Same with assignment. If you try to assign a unique pointer that already exists based on another unique pointer that already exists, that's the assignment operator, and that is not supported either in unique pointer. Okay. Okay. Any questions on that? Okay. So just briefly mentioning move and swap. So as I said, there are kind of some get out of jail things with unique pointers where you can change these values. And one of them is called move semantics. It's a very large and powerful topic, goes way beyond just unique pointers. We won't go through it in a lot of detail unless we get extra time at the end of the course. But it's one nice thing to be able to access when you're dealing with unique pointers if you need to do something. So we're going to do a little exercise where we do a move, and I think a swap, just to show you how those things are done. But basically, if we have two unique pointers, and let's think of them as called red and green, and those two pointers are on the stack. So in other words, the instance of unique pointer red and the instance of unique pointer green are on the stack, but they're going to manage something on the heap called red, a string red, and a string green, right? So the instance of the unique pointer is red, but it's managing some raw data of string type, actual container on the heap called red, right? So if I have these two things, we can swap those if we want. So we could say red.swap green, right? And those two things would swap places, which is pretty cool to be able to do, right? Or I can just say from the library, I can swap and then list those two things that way if I want, okay? So that's the swap. It's one of the few ways you can modify a unique pointer. And it's doing that just by changing the raw pointers. There's no copying or moving the data around. It's just going inside of those unique pointer instances and swapping the raw pointers. So they just end up managing something different. So it's pretty efficient to do, okay? So no heap data is being deleted or moved around, which is nice. And then move, kind of same kind of thing. If I have two of these unique pointers that are managing a string container on the heap, right? I can actually move one to the other, right? So if I say green equals move red, what I'm really saying is throw away what green was managing. I don't want it anymore. And I'm going to start managing red. So green will start managing red, and that will automatically nullify the red pointer. So all those things happen for us automatically, which again is just one of those nice things is about having kind of this fuller service class where it's going to manage all this stuff for us, right? And presumably, if you're going to say green is going to get red, you know, I want green to manage red, you want to delete the old thing that green was pointing to because you don't want to have a leak. And then you also want to nullify this class here, right? And none of those things would happen if we were just working with raw pointers, right? If I said green equals red and they were both raw, you know, old school pointers, we'd have a memory leak, and then red here would still be pointing to something, and you know we have a risk of some sort of a crash or overriding something down the road. So this is just another way the unique pointers helps you manage that. Okay, so that's the move. So swap and move; those are two things that you can get away with there, right? So we're going to actually now formalize this class in our next exercise. We're going to call this class color. Color is going to have a member named name, which is just a string name, right? So rather than having a unique pointer that points to a string, we're going to have a unique pointer that points to a class here, right? And that class is going to have a color name inside of it, right? And then we've got a destructor that's going to say goodbye whenever this class goes away. So that's kind of one of the reasons we're formalizing this thing in the class. So we can kind of see that stuff. So what we'd like you to try to do and see if this makes sense to you. It's a little bit involved. I'll get you the links to these in chat in just a second. But the idea here is we'd like to create two classes of colors on the heap and have them managed via unique pointers. And we'll name those red and green. And then we're going to print out the names of the colors via the arrow operator, right? So we'll be using the instance name and using the arrow operator to get at the pointer's instance and then print out what its name is, which is a public member of the color class. And then we want to use the move semantic to move the red instance of the color class to the green unique pointer and then just print stuff out. And then watch and see what the destructors print out as you go. So you can kind of reinforce your understanding of what's going on here. Okay, so bear with me 1 second. I'll get you the link here in the chat window. If I can find the chat window. There we go. So there's the link for the practice, and I'll pull up the link for the solution as well. Okay, there we go. All right, and bring that monitor back up. Cool. All right, so we'll give a few minutes on that. Let me know if you have any questions. Incidentally, one of the reasons people like the move semantics so much, and it applies in a lot of different areas, is it essentially is a very fast way of transferring references rather than transferring data. So a lot of default copying goes on in C++, which, you know, we've spent almost the first half of the course just doing without even realizing it. but that's a very inefficient thing to do. So if you're trying to write really efficient code in C++ and you're dealing with class instances, you definitely will be considering the move semantic to optimize things. So it's something to dig into a little bit more if ever you find yourself working on larger projects and you want to be as optimal as possible. I'll roll it back so you can kind of see some of that syntax too, if anybody wants to see the move syntax. Or is it right here, right? Right. Leave that up for just a minute. Okay, maybe another half a minute. Just back to the page. So if you do get it running, so let's take a look at the code then. If you do get it running, you should see your destructor confirming what's going on there. But let's take a look at the code kind of one chunk at a time. So here's all of our unique pointers that we're creating, red, green, and yellow. And each is really just managing a instance of the color class. And the reason I created the color class was just to have you have to experience one more level of indirection. Remember that when we actually create a unique pointer, we have to pass a pointer into the same kind of a thing that's the template for the unique pointer. So we need a new color here, right? And then the color constructor needs a string that it can initialize for the name of the color that it's managing, right? So all of that thing is a little intimidating, but we're creating a red pointer of type unique pointer color, and this is how we're initializing it in that case, right? We could also do it this way, right? We could say green and then just pass it in through the constructor for green that way, right? And that would be the equivalent way of setting up a unique pointer. And then in the case of yellow is null right there, right? But we could come back after that and reassign yellow through construction, some brand new value if we wanted to, that's fine. If I do this second line here, it's actually going to destroy yellow 1, right? So we should see yellow 1 going away, right? And if I do it again, I'll see yellow 2 going away, etc. So these things that are on the heap are going to be cleaned up whenever we try to reassign a value here to yellow, which is just one of the nice things that we get with the unique pointer class. Okay, so that's just showing you that indeed you can make that kind of assignment and it will clean up things for you. And then we can go ahead and print out the names of each of these. This is just confirming what we already know. If we want to print out the green name, we're saying green, which is an instance of the unique pointer, arrow, which is overloaded, is getting at the name member of that color class. Okay, so even though green is not a color class, it's a unique pointer class. As we've said many times, the arrow is going to be overloaded and bypass that and get at the actual class instance that we created up here inside of this constructor. Okay, so that's what we had before, and we couldn't do an assignment like that because we're not allowed to do that with unique pointers, but we can do the move, which swaps the raw pointers. And now if we print that out, we can see what the name is. Okay, so that's just a little demonstration of how we can move stuff around and a little more look at how we can manage some of that syntax up there. Okay, any questions? Okay, cool. We'll press on. How are we doing on time? I think we're going to do okay today. There's just some high points, just to remind you if you come back and look at this. Incidentally, there are 3 different ways we could actually create one of these things. I tried to represent that in the code, but just calling it out here again, I could create a unique pointer red that's not defined and then thereafter construct something. I could also do it with this assignment here, where I'm assigning it equal to a temporary unique pointer that's sort of created and assigned to that, or I could do it through the constructor there as well. Okay. Okay, and there's our move. Okay. And so that's what we did basically, right? We saw on the previous slide and set that to null. Okay. So we're going to move on then to shared pointers, and we'll see. We may only get through shared pointers today. I won't push it too much because the weak pointer stuff is a little bit hard to wrap your mind around. But shared pointers, a lot of what we learned already in unique pointers applies, right? With the addition that we can actually have one thing on the heap that is managed or referenced by more than one shared pointer, which is a lot of the examples we work with when we're dealing with code in general, and specifically in homework 7. Homework 7, hopefully you recall that a piece of the puzzle is going to be pointed to twice. It's going to be pointed to by the pieces array, which is that randomized collection of pieces that you kind of collect as you read from the text file. That's kind of like our box of pieces in a jumble. And then once you put it in the grid, you're going to be pointing at that same piece from one location in the grid as well. So each token in homework 7 will be pointed to twice. So if we were going to convert that over to shared pointer or over to smart pointers, we would most certainly want to use a shared pointer in that case so that we can maintain both of those pointers. Now, we could redefine it and say, hey, when we move it over to the grid, we want to pull it out of the pieces array. And then in that case, we'll use a unique pointer. But we're going to follow the shared pointer model just going forward. So let's take a look at the syntax. It's all of the same stuff really that we saw with unique pointer, except that when we point a shared pointer at something on the heap, we get a count, what's called a reference count, that's managed by the shared pointer. It keeps count of how many other shared pointers are pointing to that exact same item on the heap. So if I add another shared pointer to it, they're all going to share or keep track of the same reference count. So that reference count will live in the instance of each shared pointer, and it will be synchronized. So every time we add a new shared pointer to that same chunk of memory on the heap, the reference count for each of those pointers goes up in sync, so that they all know there's somebody else out there potentially or not currently pointing at that piece of memory. So that's the key difference with shared pointers, is we get that reference count. And the reason is because let's say we want to delete one of those shared pointers. Like let's say you want to delete your pieces array in your puzzle, homework 7. And let's just say that you did all that with shared pointers. Well, we wouldn't want it to go ahead and necessarily delete the pieces of the puzzle because they're still referenced by the grid. So the shared pointers will do that automatically. I can delete the shared pointer here, and if there's somebody else still pointing to that int5, it's not going to try to clean up that int5. It'll just decrement the count down to 2, right? So now everybody who's still kind of active and pointing to that has a reference count of 2. And the shared pointer is no longer part of that. It's actually retired. It's no longer valid, right? So we can just keep deleting those things. And in the last deletion, it's of the last shared pointer, the last one, it's kind of like the last person out of the room should turn off the lights. That's really what's going on here with the final shared pointer. It's going to do the cleanup for you if it knows the reference count is going to be 0 after it goes away. So that's a really cool thing about shared pointers, right? And they have all the other good stuff that comes with them too. They'll, support copy assignment, right? So if we want to actually do a copy of these things, we can. Now it's a shallow copy, granted, it's not a clone copy, but it'll actually, because they're shared pointers, it'll actually allow us to do that copy so we can have multiple references to the same piece of data. So here's a little bit of look at code. There's a null shared pointer. There's a shared pointer pointing to integer 5 on the heap. We can print out what that shared pointer points to get the 5. We can then create a shared pointer too that points to the same thing as S pointer, right? So now you can see the use count goes up. Those little animations are so hard to make too, I gotta tell you. PowerPoint does not like doing that kind of stuff. So basically our use count in both of those goes up to 2, right? Right. So because we're just reusing that same shared pointer that was already initialized to something on the heap, right? And then if I reset one of those, the shared pointer count for the ones still participating drops down. This one is set to null, so its use count doesn't matter anymore, right? And we can still print out what S pointer 2 points to with the star SPTR until we reset that thing, and then that goes to 0 and it cleans up the memory, right? So that's some pretty cool stuff. You'd be surprised at how vital it is to have access to that kind of a system when you're dealing with large quantities of things that you create. You know, a bunch of people might be referring to you as a friend in their Facebook friends list, right? So, but you know, I guess probably not a good analogy because you wouldn't ultimately be deleted. But in a situation where the last one needs to delete you, you know, you would need a system like this to let you manage that more cleanly. Okay. So, and all the other things that we've seen work with the shared pointer, so we can check for its nullness by saying if is not defined, then print out null. And we can also just check the use count to see how many other pointers are using it. If 0, then of course, then it's null effectively. Okay. So that's shared pointer. And there's one other thing I want to introduce before we jump into our exercise. And this is a shortcut, right? So when we create a shared pointer, there's an awful lot of syntax going on here. And in particular, right here, you see where we say new int 5 there? We could have just passed in an already existing pointer to that as part of that constructor, and the shared pointer wouldn't know. And that's kind of a backdoor way that opens up possibilities for bugs, because you might have actually had some other unshared pointer managing that chunk of memory. And now you're passing it into the shared pointer. And it's possible those two would conflict. One might delete something when the other didn't know what was going on. So they invented this idea called make shared. So make shared, so this is the standard way of doing things, right? Shared pointer green gets a newly constructed string called green. But we could also do it this way. We could say shared pointer string of green equal make shared string green. So what's the difference here? Let's take a look at how these things lay out. So in this case, we're passing in a pointer that we create. We create it in line, right? But it essentially creates it on the fly and passes in a pointer to this constructor for the shared pointer. Here, we're letting the make shared utility do that construction for us. So we're telling make shared, hey, I want you to go ahead and create an instance of a string, and here are the arguments to the string constructor. Okay, so this is a little confusing because where here we'd have to feed the string green to the actual string constructor, here it's implicitly understood that make shared is going to take those arguments and feed them into the constructor for whatever type you put here. So this accomplishes the exact same thing, but it does it more safely because there's no way the outside world can get a pointer to that instance that's put on the heap. Make shared creates it behind the scenes, and there's less risk of someone having access to that pointer and doing something bad with it. So these two are totally legitimate. They do the same thing. A little less syntax here, and in theory, a safer way to do it. And I introduce it just because it gets used a lot, and if you see it, you might think, hey, wait a minute, what's going on here? And it is a little confusing, so I'll try to give you lots of samples to reinforce your memory of that. But we'll look at doing that in our next project here, just to get a little exercise with it, okay? So, and just remember that that is the constructor arguments for string, where that arrow is, okay? Otherwise, we do it that way, okay? So, right, so this would be the other way that we could do it. Sorry, this last thing in the upper right corner there. So if we said string SPTR equal new string, we could actually, in fact, pass in SPTR to that and we'd have a little handle in the outside world on this little chunk of memory that is being managed by shared pointer. That's the risky part, right? If we allowed somebody to do that. That's why make shared is considered to be better, right? Okay. So let's try this. So we're not creating color instances here. We're just creating string instances. So create a shared pointer, if you will, to a shared pointer named green that owns a green string. Okay. And then use make shared to do that. And I'll roll back to that previous slide and I'll give you a link here in a second. And then create a shared pointer named extra that starts out life as null. And then go ahead and assign that to green. So now we'll have two pointers, two shared pointers pointing to the same green string on the heap. And you should be able to print out the use count for both, for extra certainly. And then if you set green to null, check and see what the use count is at that point. You should see the use count go down because it's basically not going to delete the green string because extra is still pointing to it. We'll let you kind of figure that out. So here, let me just get you that link. So bear with me 1 second. Copy that over, oops, to the chat. Where'd chat go? Huh. Once again, chat. Oh, so almost off the screen. There we go. So there's the practice link, and I'll give you the solution link as well. There you go. Okay, let's give that a try. I'll set the timer here for a couple minutes. See how we do. Okay, go back and give you that syntax again in case anybody wants to see that. This guy, that's what we want. So there's the two main ways to go ahead and create that stuff. Another half a minute. So the key idea again with shared pointers is that it's not going to clean up memory until the last pointer, shared pointer referring to the same chunk of memory, essentially goes out of scope or gets deleted. Okay. Let's take a look at the code there. So here's our creation of our red pointer, right? And there's our green pointer, right? They're using the make shared. So similar kind of construction. We're just using make shared here. We're manually calling or instantiating a string. Here we're letting make share instantiate the string for us, but we're just passing in the constructor arguments for the string class, right? And there's our null extra. And then when we point extra to green, the usage count on green should go up, right? So if we print that out, we should see that there are two shared pointers referring to that, right? And if we print out the usage count on extra, it should match, right? They all share the same usage at all times, right? If they're pointing to the same piece of data on the stack. And then if we nullify green, it's just going to reduce its usage count. So now extra, so green's usage count goes to 0, but null's goes down to 1 because there's only one pointer now participating in that particular chunk of memory, which is the extra pointer, right? So that's kind of the gist of shared pointers. It's pretty straightforward, really. You just have to remember that all of these things are linked together based on what address on the heap they're managing. And there's a counter inside of all the shared pointers that keeps track of that. So it's pretty interesting. I'd be curious to see how they actually implement it under the surface, but it works quite well. Right? So there's kind of an animation of what's going on when we actually do that initialization of green, and then we set it to null, right? And our usage count drops down. Now red's usage count, of course, stays at 1 the whole time because we haven't done anything with it, right? So every unique piece of memory has its own usage count, okay? So now if we were to try to do, let's see if we're going to try to sneak in one more. So we're going to do one more shared exercise. So this idea is we're just going to do the same kind of thing, but we're actually going to formalize a class, right? So the idea here is we're going to create a tool, a class called tool that we want different people to use, right? Our shared pointer is going to be referring to an actual tool class rather than an integer number. And this should be a direct extension of what you just saw, but sometimes throwing the class in there throws people off. So let's take a look at it. So our constructor for our tool just wants a string name for the tool, like a hammer or a saw or a tape measure or something like that. So in main, we want to create a shared pointer called Jeff. So I'm the person using the saw. So that's kind of the analogy we're going for here. And there's no string Jeff. It's actually just the variable name Jeff. I'm naming myself after the shared pointer, and I'm using the saw, right? So I can check for the tool name by saying Jeff arrow tool name or tname, right? Because that's our member of the tool class. And then I could create another shared pointer, John, right? That's going to be borrowing or sharing the same tool that I have, right? So now we've got two shared pointers, Jeff and John, that are actually referring to the same tool, the saw, okay? So just kind of highlighting that we're managing an instance here on the heap with both of these shared pointers, okay? And now our usage count is up to 2. And we could print out the name, and they would be identical in name, but also, you know, the identical member of memory as well on the heap. So if I were to use the get method, for example, off these shared pointers, I could actually compare the raw pointer on the heap and confirm that we're both managing the same piece of data on the heap. So that would work, even though we have 2 different instances of the shared pointer, okay? And there we go with that, all right? So I think, yeah, that's our tool class. Just another quick look at that. And then we put a destructor in there. So when the tool goes away, we can actually see how that goes. So what I'd like you to try to do for your final exercise here, and I'll get you the links in a second, is basically create a shared pointer, Tom, or somebody that uses a hammer, right? And use the shared pointer constructor in new to create the hammer tool instance. And then create another one, call it Lisa or another person, and then use make shared on that just to exercise your use of the make shared utility, right? And then you want to create just one more pointer, shared pointer Neo, that's going to use a different tool, brush. So all of these are just getting you used to expressing those tool constructor arguments inside of the parentheses for the shared pointer itself. Right? And then in this separate scope, if you do any of these things inside of a separate scope, and this is getting a little tricky, but it just goes to show you that the transient scope that might exist in functions or inside of the main or something like that actually does affect the usage count. So if you create these two pointers, Tia and Lisa, inside of some special scope, and that scope goes away, the usage count on that pointer is going to go away too. Okay. So let me get you the link there for that. And get back over here, bring up my chat window. There we are. So there is the practice. And then let me get you the solution as well. There you go. So give that one a try. Give you about 3 minutes on that one, and then we'll walk through the code and just kind of wrap things up. I don't think we'll go into the weak pointers today, but we'll just mention a few things before we go, okay? Okay, just another minute or so. So again, the idea of this last bullet here for this scope is just to kind of convince yourself that if you create a shared pointer Tia inside of its own scope and reference Lisa, it will increase the use count, but only for as long as Tia, the local, in the local scope exists. So as soon as that scope goes away and Tia goes away, that usage count that for that particular heap item in memory goes down as well. Okay, why don't we take a look at the code there so we can kind of get you guys wrapped up. So here's our main, and we're going to go ahead and create a pointer Tom, shared pointer Tom, to managing a tool. And here we will not be using the make shared, right? So we're doing it the original way we learned. We're saying create a new instance right here of tool called hammer, pass the pointer in so Tom can manage that shared pointer, right? As contrasted to this Lisa pointer, we're saying, okay, Lisa is going to be a shared pointer, and Lisa's going to get an instance of the make shared result from the utility. The make shared is going to create a shared pointer of a tool, and these are the constructor arguments for the tool, right? So that's what make shared does. It kind of removes the need to actually restate it's a new tool. It's like, we know it's going to be a tool. We know we're going to be calling new. Let's just give it the constructor arguments for the tool. So that's what's going on there, right? And we could have used auto for that, right? And then we'll create Neo. That's just another exercise. But inside of this local scope, if we create Tia and we borrow or point Tia at the same thing that Lisa is pointing to, we'll increase the usage count only for as long as Tia is in scope. And once we go out of that scope, we'd see that usage count come down again, or the reference count, okay? Okay, any questions on shared pointers?
That's kind of our wrap up page right there, kind of giving you the animation of what's going on, right? Lisa comes into scope, or Tia comes into scope, and then Tia goes out of scope, and then usage count goes back down again. Okay. Any questions? Okay. Okay. So there's kind of all of the key methods for shared pointers that you can use to just check on things. I think this last one might be a little confusing. We didn't talk about this, but we can see if it's unique. In other words, is there anything else actually sharing that shared pointer? So if you ever need to come back for reference to that stuff during homework cake, that's one place you can go find that stuff. Okay. So we're gonna stop it there. We'll come back on Tuesday to finish up on weak pointers and lean a little bit more into homework 8, but I don't want to bury people too much. So we'll probably give some hints out for homework 7 as well. People are looking for some help on that. Any questions before we go? Does anybody have any questions about the schedule or process so far? Okay. All right, cool. And although I missed the beginning of the lecture on record, I did start recording it after about the 10th slide. So as soon as that thing is processed in Zoom, I'll send you the link out on that as well. Is that stuff helpful to folks? I assume it is. It looked like it came out pretty good. So I'll just keep doing it as long as I can remember it. And if you guys have any feedback, again, please feel free to send it my way. Okay. All right, well, with that, I'll let you go. Thanks, everybody, and have a safe and sane weekend.